Units. Units are really, really important. Back in 1999, NASA lost a $125 million spaceship. Lots of time and money invested into this thing. It was supposed to go and orbit Mars, and we were supposed to get all this great information. But it got too close. Its orbit was not at the right distance, and it got too close and got pulled in by the gravity of Mars and burned up. Like, not long after it got there. So, of course, there's an investigation, and the conclusion was the root cause of the loss of the spacecraft was a failed translation of English units into metric units.
What?
Right?
It was by one of the big aerospace companies that they did all of their measurements in their own standards, which doesn't make sense for an aerospace company.
No, it doesn't. The specific story I heard was that, they needed to adjust the orbit, and so this team was in charge of, adjusting controls on the orbiter, and this other team was in charge of calculating what those adjustments should be. One team was using inches and one was using centimeters.
We're not on the same page.
I don't know.
Why are we
But-
using inches to begin with?
I don't know. You guys are asking some great questions. Inches are stupid with their fractions. Oh, ugh, don't get me started.
They are easier to measure, like without like, cause you can estimate them, but they're harder to calculate with. Because you can measure like an inch with your thumb.
Yeah, but you could figure out on your body a part that's a centimeter also. You could.
Yeah.
Yeah.
Harder.
Yeah, but yeah, the calculations are much easier with metric units. A question I also have is, why don't students write units on their work? Because when you don't write the units, then you sometimes miss that, I needed to change this unit into this other unit before I continued on, and so you do all these lovely calculations and you come up with the wrong answer because your beginning and end weren't in the same units. So thankfully the consequences for us are not this great, but units are really, really important. There are two common unit systems, the metric system and the English system. And what scientists use is called the International System of Units. The International System of Units is almost identical to the metric system. Really, the only difference is what they consider the base unit for some of their quantities. And in my opinion, that slight difference is not even worth talking about.
They use a kilogram, right, instead of a gram.
Yeah, they use a kilogram instead of a gram. And they have a reason, but yeah. So these are quantities that there are units for, just base units in these systems. So length measured in meters, mass measured in kilograms, time in seconds, temperature in kelvins, amount of substance in moles, and the last two are there, but we're not going to use those in chemistry this semester. So it's helpful to have a rough idea of how big these units are, right? So if you do a calculation and you end up with this person being 7 meters tall, is that even possible? A meter is essentially a yard, which is 3 feet, so 21 feet tall. No, nobody's that tall. Okay, so there's some details about it, but I'd like you to know that a yard and a meter are about the same size. Mass is measured in kilograms. Again, it's good to have an idea of the size. So a kilogram is a little over 2 pounds. So if you take your mass in pounds, divide by 2, that's going to give you the rough mass in kilograms. So a 130-pound person would have a mass of 59 kilograms, which might, sound nicer to you because it's a lower number, but you're going to wear the same size pants, right? Weight is different than mass. Weight is the force of attraction by gravity on an object. And it's proportional to the mass, but it also depends on the strength of gravity on whatever planet you happen to be on. We're all going to stay on planet Earth this semester, right? Nobody going up with Elon Musk or anything? So we can use mass and weight interchangeably, but in the back of our heads, we have to understand they are not identical. In chemistry, we typically use the gram because it's a smaller unit and it more closely matches the size of things that we weigh, right? So a gram is can be remembered this way. A nickel, which is 5 cents, has a mass of about 5 grams. So 5 grams is the mass of a nickel. It's not very big, right? It's pretty small. The second is the same second that you know about. You know, there's the 60 seconds in a minute thing. Scientists avoid using minutes and hours because there's 60s involved instead of tens, and the conversions are messy. So we'll use seconds. And there's the details about how they currently define a second. For temperature, the SI unit is Kelvin. Now, temperature measures the average kinetic energy of a substance. So I mentioned on Tuesday the 3 states of students, right? Solid, liquid, and gas. What state are you in right now? Solid. Because you're sitting still relative to each other, right? And we're close together. So when we have lab and we're walking around, then it's more like a liquid. So you'll say, well, how does a solid have a temperature then if it's not moving? The particles are moving within the solid, right? You're breathing, you're checking your notes, looking at this, that, the other thing. Everybody's moving. Now imagine it's an hour from now, and you're like, when is she going to stop talking? I need to use the facilities. And you start to get antsy, right? It's like, I can't sit still any longer, and everybody's just, well, that's like an increase in temperature for the solid. So a warm solid, its particles are just all jittery, and a colder solid, they're calmer. So temperature is a measure of average kinetic energy. And then the other important thing about temperature is it determines the direction of thermal energy transfer. Thermal energy always goes from the hotter object to the colder object, and that matches with what we experience in real life, and that's called heat. Heat always goes from the hot object to the cold object. So 2 other temperature scales, the Fahrenheit scale and the Celsius scale. Fahrenheit is what the weatherman uses, and if they say it's going to be 104 degrees, they mean degrees Fahrenheit. Or if you look at a recipe, bake at 350 degrees, it's Fahrenheit. On the Fahrenheit scale, water boils at 212 and freezes at 32. This is kind of typical of an English unit. The numbers are just kind of wonky, right? Where do they come up with these? On the Celsius scale, which is a metric scale, water freezes at 0 and boils at 100. You're like, well, that's awfully convenient. Well, it's convenient because we took those temperatures as a basis for making the scale, right? It's easy to have something that's 0 degrees Celsius. You just put it in ice water. Ice water is always going to be 0 degrees Celsius. And so, like, if you're trying to make a thermometer, and, you know, back in the day when they didn't have factories and stuff to make these things for you, how do you calibrate it? Well, 0, that freezing point of water, is a place that you can get to very easily. The other place is boiling water. When you boil water, it's always 100 degrees Celsius, and so you can use that as the other end of your scale. And then they divided this into 100 separate degrees. Both of these scales have the potential for negative numbers. There's a third scale, the Kelvin scale or the absolute scale, in which negative temperatures are not positive. Well, of course they're not positive. They're not possible. Negative temperature, that's not the stupidest thing I've said today. Negative temperatures are not possible because in the Kelvin scale, 0 is defined as the absolute 0, the lowest possible temperature, which would be the temperature at which all motion stops. The atoms are not even vibrating. You might even argue that the electrons aren't moving. I'm not sure. That's getting a little too far into physics. But so they defined that as absolute 0. They kept the unit size the same. So a Celsius degree and a Kelvin are the same size. They're just offset in where 0 is. So on the Kelvin scale, water freezes at 273 and boils at 373. On the Celsius and Fahrenheit scales, we have a difference in where 0 is, and also a difference in the size of the degree, and so the conversion is a little more complicated. So to convert between Celsius and Kelvin, we need this equation. It's an algebra equation to convert between. The conversion between Celsius and Kelvin is a little simpler. We're just adding 273.15. These equations will be given to you on an exam, but we do need to know how to use them. And there's some questions on today's worksheet about that. So let's do this example. Gallium is a solid metal at room temperature, but will melt to a liquid in your hand. The melting point of gallium is 85.6 degrees Fahrenheit. What is this temperature on the Celsius scale and the Kelvin scale? So it's a good idea, after you read the question, highlight any numbers that are present, include the units, and then look for what are they telling me to find? Well, we want the temperature in Celsius and in Kelvin. So converting temperatures always requires an equation. So for part A, we're looking at the relationship between Fahrenheit and Celsius. So we're going to use that equation. The temperature in Celsius is equal to the Fahrenheit temperature minus 32 divided by 1.8. So we have our Fahrenheit temperature here, so we can put that in. And we're going to subtract 32 and divide by 1.8. Get your calculator out and do this so that you make sure that you're communicating correctly with your calculator. My calculator is showing me 29.777, whole bunches of sevens. 7 repeating. If you're not getting that answer, you probably accidentally did 85.6 minus 32 over 1.8. So you need to use parentheses up here, or after the subtraction, press the equals and then divide. So that's what my calculator is telling me. Now, we learned about significant figures on Tuesday. This one is going to be kind of messy because we have subtracting and we have division. So we'd have to look at the two individual pieces, and we do this a lot, and it's just kind of annoying to have to do that. Because the Fahrenheit and Celsius degrees are similar in size, a Celsius degree is like less than 2 times bigger than Fahrenheit. What we can do is kind of a shortcut. Look at your original temperature and see what decimal place it ends in. This ends in the first decimal place. So I'm going to convert my temperature, and then I'm going to round the new temperature to the same place. So I'm going to round this to 1 decimal place also, and I can preserve this precision that way without having to think too hard. Yes?
Once there's more numbers involved in temperatures, isn't it the one with the lowest amount of sig figs that you use in your answer?
Well, if you're just converting a temperature into a different temperature unit, this always works.
Okay.
Yeah, if you're multiplying temperatures, I don't know why you would do that, but, or if you're doing other calculations, then yeah, you have to consider that. Yeah. So then the next part wants us to find that temperature in Kelvin. So maybe you didn't notice, but there's no equation given between Fahrenheit and Kelvin. We don't do that very often, and it'd be a pain to have another equation. So if you need to go from Fahrenheit to Kelvin, you just go from Fahrenheit to Celsius, and then Celsius to Kelvin. Yeah.
You could just take that equation and then subtract 273, I think. So that would just be, like, to cut the middleman out, so you just say,
Yeah, so essentially what you're saying is you can combine these two things, and what I'm saying is we're not gonna worry about trying to combine them, we're just gonna do them quick,
Okay.
separately.
okay.
Yeah. There's a lot of times where there is a shorter, more elegant way to do something, but we don't do it that often, and so there's really no point in learning how to do something you don't use very often, when it's faster to just do the thing you know twice. So we're going to use that equation. Kelvin is equal to degrees Celsius plus 273.15. So I'm going to take the answer to part A to find the answer to part B. Should I use the 29.8 or the 29.777? Yeah, I want to keep those extra digits. This is rounded, right? Which is perfect for a final answer. But this is a good illustration of why we should always write down at least 2 extra digits and then round it. Because if you need that number later in a calculation, you can go back and use the one with 2 extra digits, and 2 extra digits is enough. You don't need any more than that. If you want to write them all down, bless your heart. So 29.777 plus 273.15. And I'm going to do the same thing here, Celsius to Kelvin. This one came from that one which had 1 decimal place. This one we rounded to 1 decimal place. This one we're also going to round to 1 decimal place. But I'm going to write down the 2 extra digits just in case I need it for something later. And this is 302.9 Kelvin.
I kept 2, so it would have been wrong.
What do you mean you kept 2?
2 decimal places.
Um,
Instead of 15, I thought I had to keep 2.
You've got an extra digit on there. So in terms of sig figs, it's wrong. You can follow the strict rules of sig figs for this, and there's a couple of places where there's a weird suspension of sense where you can gain or lose sig figs by converting units, which shouldn't be possible. And that's just one of the, sig figs are not the absolute best way. They're just the easiest way. So for temperatures, just round to the same place. If your temperature was 25, it ended in the ones place, and you convert that to something, round that answer to the ones place. Scientific notation should be something that you've learned in your previous chemistry class. It is outlined in Appendix 1A, and there's also a module on Mastering Chemistry. It'll help you review what scientific notation is. Scientific notation lets us take really big and really small numbers and express them in a more compact way. So we don't have to have, 20 zeros after a number, right? And we do that by factoring out tens. So the metric system and the SI system do that also, but instead of showing it in scientific notation, we're going to represent those factors of 10 by using prefix multipliers. The multiplier just changes the size of the unit by powers of 10. So for an example, kilometer has this prefix kilo in front of meter. The prefix kilo means 1,000 or 10 to the 3. So then 1 kilometer is 1,000 meters or 10 to the 3rd meters. When we're reporting a measurement, we'd like to use a prefix multiplier that's close to the size of the quantity we're measuring. We usually use a unit that is similar in size to the thing we're measuring. Right? If I wanted to measure the length of my Apple Pencil, would I use miles? No, it would be ridiculous. What would I use? Inches. You know, if I'm being, a stupid regular person and not a scientist, I would use centimeters, but to just, illustrate the point. Why do we use inches for this? Because then we're going to get a reasonable number. It's going to be like, 7-something inches instead of like 50 bazillion or 0.00000007 or something, right? So in the metric system, we have those base units, and then instead of having a bunch of units like inches and feet and yards and miles, and there's fathoms and furlongs and all kinds of other things, right? And the relationships between those are all crazy. Like 5,280 feet in a mile, 3 feet in a yard, 12 inches in a foot. It's all over the place. In the metric system, we're going to use the same prefix multipliers on all the units. So we learn the same prefixes and we can use them for everything. It's much more efficient. And we don't have any wacky numbers to remember. So this is a list of SI prefixes. If you've looked at that list of stuff you're supposed to memorize, this should look a little familiar. Oh, that wasn't the one I wanted. Now, you may not have time or the willpower to memorize all of these. That's okay. Those are the 4 most important ones. We will use those a lot during the semester. It's definitely worth your time to memorize those, okay? So the prefix, centi, it's abbreviated with a lowercase c. It means 10 to the minus 2. You kind of have to watch out for the m's because we've got mega and milli and micro. They all start with M. Well, mega makes it bigger. It's a capital M. Milli makes the unit smaller. It's a lowercase m. Now we ran out of English m's, so we're going to use a Greek lowercase m, the mu. Okay. So how long is 4.5 megameters in meters? We can substitute the meaning of mega for the symbol. Oops. Writing in highlighter, just never a good idea. So on that table, mega is 10 to the what? 10 to the 6. And a good way to get these in your head better is, when you find yourself needing to know what one of these is, don't just go straight to look it up. Try to guess what it is first, and then check by looking it up. So it's 10 to the 6. So here, instead of, I really shouldn't talk while I'm writing. Instead of writing that M, I can write what it means, times 10 to the 6 meters. Yes?
To convert a unit like that, well, you wrote it out, so you would have to do.
This is kind of a shortcut way of converting units that have prefixes to the base unit.
Okay.
And if you had, that was writing with the eraser. Let's say you had 492 megameters. Well, that's going to be equal to 492 times 10 to the 6 meters. Now, is that improper scientific notation?
No.
No. Could we use it in the calculator? Yes, we can. Okay, so you don't want to leave an answer like that, but if you want to use that as a shortcut in a calculation, you're welcome to do that. Not sure why, but it just suddenly got too warm in here. One of these days I'll remember to plug the fan in before I start talking. So there's a question on the worksheet that has you do some things like this. And we could also go the other way. Here's a number written in scientific notation, 7.13 times 10 to the minus 9 liters. And how many nanoliters would that be? Well, what does nano stand for? 10 to the negative 9. Nano? Nino? So 7.13 times 10 to the minus 9 liters. Instead of this part, I can write lowercase n. Okay? So we talked about base units. There are also derived units, and these are combinations of other units. So there's no metric unit of speed, right? You'll use 2 base units to describe that. It might be meters per second, right? So those are derived units. Volume measures space and also uses derived units. It's going to use a unit of length cubed. So this is a picture of me. I was very fortunate and got to go to Oslo one time. And so, of course, I visited the Science Museum. And they had this cool box that you can sit in. Well, how big is this? Well, it's 1 meter on a side. Let's see, let me get the other dimension in there. Oh, I know what, I did that wrong. And this is a meter. And this is a meter. So the volume is the length times the width times the height. 1 meter times 1 meter times 1 meter, which is 1 cubic meter. So any unit of length when cubed becomes a unit of volume. Cubic inches, unit of volume. As in the kitchen, where we tend to use different volume measurements for liquids and solids, we also have some volume units that are specific to liquids. And so those are going to be liters and milliliters. And I think everybody knows how big a liter is. Well, everybody knows how big 2 liters is, right? 2 liter bottle of soda. How big is a liter? Half of that, right? And then milliliter. So 1 milliliter. What does that prefix milli stand for? Yeah, 1/1000th or 10 to the minus 3. So a milliliter is 1/1000th of a liter. So here we have an illustration of a liter. We have this cube made up of smaller cubes. Each of these little cubes is a centimeter on a side, and so the volume of that small cube is going to be 1 cubic centimeter. Length times width times height. Well, yeah, I left out the 1. There we go. And there's 10 little boxes across this way, and 10 deep, and 10 tall. So the volume of the big cube, then, is 10 centimeters by 10 centimeters by 10 centimeters, which is 10 to the 3 cubic centimeters. So that's 1,000 cubic centimeters. One milliliter is exactly the same as 1 cubic centimeter. They're literally just different names for the same thing. And in medicine, there's a third name for the same thing, cc. Give him 3 cc's of this, stat, right? cc is how doctors and nurses refer to cubic centimeters. The first letter, cubic is centimeter. So they call it cc. In chemistry, we call them cubic centimeters or milliliters. So 1 milliliter is 1 cubic centimeter. So this is telling me that this volume is equal to 1,000 cubic centimeters, which would be the same as 1,000 milliliters. And one way I could convert that to liters is by replacing the milli with what it means. And if I have 1,000 and I multiply by 10 to the minus 3, I end up with 1. So this is a liter. A liter is 1,000 milliliters. Here are some common units and their equivalents. So this is a great chart to refer to. You might want to take a screenshot of the slide on Canvas or a picture from your book and just, keep it as one of your favorite pictures so you can pull it up and look at it. These are really all the conversions that you're going to need in this class. The one thing they didn't put on there specifically is this one. 1 cubic centimeter equals 1 milliliter. That's supposed to be obvious, but it actually is not obvious to students. So we have different length units, different mass units, and different volume units. Most of these are looking at English to metric. So here an English unit ounce to metric unit grams, here a liter to a quart. So most of these conversions are not exact. Yeah?
Will we be given like this information for a test on a piece of paper with like a periodic table, or will we be on our own to memorize it?
There are only a couple of these that I expect you to memorize. One of them is the inches to centimeters. So that guy right there. Aside from that, I hope that people know there's like 12 inches in a foot and 3 feet in a yard and stuff. But if on an exam you're like, dang it, I cannot remember how many feet are in a yard, just come up and ask me, okay? Because that's not the point of all of this. If you need other conversions on an exam, they'll generally be given to you. Okay.
Like within the problem.
Within the problem. Yeah. Yeah. So this is an exact relationship because they actually redefined the inch so that it is exactly 1.54 centimeters. They're tired of the other digits, I guess. There's another place you can get conversions. We're going to find out about this eventually, so I'll just tell you. The famous or infamous green and yellow cards. So this yellow one has a whole bunch of conversion factors here. On the other side, it has a very useful periodic table. It also has the metric prefixes in here and some of the constants. This is way more stuff than you need for my assignments, okay? You're better off just looking at this little simple table. And then there's this other one that has other useful information. There are digital copies of these on the Canvas page in case you had one and you lost it and you need it. They are in the little plastic holder up there. If you want to take copies and stick them in your binder, feel free. The reason I discourage you from using these relationships, one is that the way they're written is sometimes confusing. And the other thing is, I'm going to be teaching you today a technique called dimensional analysis. It's a method of converting units. And I'm not doing that just because you need to know how to convert units. I'm doing it because it's the easiest way to do some chemistry problems later called stoichiometry. And so I want you to learn the technique on just some simple units before we start getting into grams and moles of different substances. So on the worksheet today, you're going to have to do some unit conversions. Now some of them you could maybe just look up. The other thing is you can ask Google, right? You could ask Google or Siri, how many tablespoons are in a gallon, right? And it'll tell you. So you could bypass all the steps in the unit conversions on today's worksheet. But that would mean that you don't learn the technique. And then when you need the technique, because Google can't help you when I say, well, how many grams of hydrogen is 2 grams of oxygen equivalent to, because they don't know which reaction we're talking about, then you're going to be in trouble. Okay? So if you want to check your answers by looking them up online, sure. But don't rely on getting conversion factors from the internet, okay? Just use these guys. Okay. Another derived unit is density. So density is the mass of a substance divided by its volume, or written with variables d equals m over v, mass over volume. Common units for liquids are grams per milliliter. There's that mass unit divided by a volume unit. For solids, we typically say grams per cubic centimeter. But cubic centimeter and milliliter are the same, right? They're the same. Density is a physical property that depends on temperature. There's a question on the worksheet about this. Density depending on temperature. Well, density involves 2 quantities, right? Mass and volume. And so if this is telling us that density is going to change with temperature, that means one of these has to change with temperature. Will the mass change if you heat something up? No. Will the volume change? Yeah. It might change just a little tiny bit, but the volume can change with temperature. So whenever we see a density given, they're going to specify a temperature. So these are densities at 20 degrees Celsius. If you were wanting to work with these at 100 degrees Celsius, you should not rely on these densities because they're probably significantly different. Now, if you were close to that, 25 degrees, yeah, you're probably fine. We also don't need to memorize densities. It's really interesting. You get 2 different kinds of students. There's the ones that won't even memorize what you tell them to memorize. And then there's this other group that think they need to memorize everything. And they'll say, do I need to memorize that table? So I'm going to tell you right now, no, you don't need to memorize the table, okay? There's only one of these that is worth any space in your head, and that's this one, water. At 4 degrees Celsius, water has a density of 1.00. So there may be times where you're doing some sort of a calculation and you need the density of water. If they don't give it to you or make a big deal out of it, just use 1. There are other times, like we're going to do a couple labs where we need the density of water, and we're actually going to measure the temperature and look up the precise density at that temperature because we're trying to do more precise work. I'm pushing the button and nothing's happening. There we go. So in addition to chemical and physical properties, we can also say there are intensive and extensive properties. An intensive property doesn't depend on how much substance there is. So the boiling point. The boiling point of water is 100 degrees Celsius. It doesn't matter if you have a cup of water or a whole swimming pool of water. The boiling point is the same. Other properties do depend on how much stuff you have. The mass of a cup of water versus a swimming pool of water, those masses are different, right? So intensive properties are like intrinsic qualities. This substance always has this quality. And extensive are like more external. It does depend on how much stuff there is. Because density is an intensive property, it can be used to identify things. So here's an example. This is what we call, they called it when I was a kid, a story problem. Because there's a story. So you gotta just read the story, even though most of it is totally irrelevant. A man receives a platinum ring from his fiancée. Before the wedding, he notices that the ring feels a little light for its size and decides to determine its density. He's probably a science nerd. He places the ring on a balance and finds it has a mass of 3.15 grams. He then finds that the ring displaces 0.233 cubic centimeters of water. Is the ring made of platinum? So the problem-solving strategy is that you always read the whole problem, and then you go back and you highlight the numbers, because generally the numbers are going to be important. And then you're going to highlight what you're trying to figure out. Is the ring made of platinum? Well, that's going to be yes or no, and we can't just calculate yes or no from these numbers. What do we have to find out so that we can answer that question? The density. So that guy was determining his density. So that's what we need to do here, is we need to calculate the density of this ring. Calculating the density, you're going to use the density equation, mass divided by volume. What's the mass of the ring? 3.15 grams. And it says it right there, mass of. What's the volume? It is 0.233 cubic centimeters, but it doesn't specifically tell us that. So one clue that this is a volume is the unit. Cubic centimeter is a unit of volume. What do they mean by displacing? So what if you fill the bathtub all the way to the top? Don't do this at home. You fill the bathtub all the way to the top, and then you get in very carefully.
It's gonna overflow.
It doesn't matter how careful you do it. Water's going to spill out, right? Because your body has volume, and when you get into the bathtub, an equal volume of water has to leave. It's displaced. And so this is a technique for measuring the volume of irregularly shaped objects. So you can take a graduated cylinder and put some water in it. And you read the graduated cylinder and it says 10.0 milliliters. And then you put your chunk of rock or whatever in there, and it's going to displace some of the water. The level goes up. Because now what we have is the volume of the water and the volume of the thing we put in there. So let's say that this is 12.0 milliliters. Well, the volume of the object is the volume of water that was displaced. 12.0 minus 10.0, so 2.0 milliliters. So that's what it means when it says that displaces that much water. Okay, so then we're just going to do this calculation. 3.15 divided by 0.233. And my calculator's giving me a whole bunch of numbers. And what are the units?
Grams per centimeter, cubic centimeter.
Yeah, grams per centimeter cube. We don't need to try to convert these or anything. You can't. They're not going to cancel out. It's just, I mean, sometimes you'll have units that cancel out. Other times you don't. If they don't, you just write them all down. Is that the right number of significant figures?
No.
No. So here we're dividing. Remember, there's adding and subtracting, we count decimal places. Multiplying and dividing, you count sig figs. So here we want to count the sig figs. How many sig figs in 3.15? 3. And in 2.33?
3.
Also 3. So the smallest of those is 3. They're both 3. So that means I'm supposed to keep 3 significant figures. So what I'm going to do is I'm going to underline the third one as a signal to myself that's the last significant figure. Do I have to write down all the rest of the digits? Absolutely not. I highly recommend writing down 2, just 2 extra digits. That will save you from rounding errors and also save you from writing down all these messy numbers. So now I'm going to round the answer. I'm looking at the digit that's getting dropped, less than 5, so 13.5 grams per cubic centimeter. That's the density of the ring. How do we figure out if it's platinum?
Check the table.
Check the table. Yeah, we'll go look up the density of platinum. And here it is, all the way at the bottom, 21.4. Not even close. That ring is not platinum. Yeah. So the answer then is no. Not platinum. Yes.
In a quiz or exam, you will specifically say put in proper significant figures, or if we were to be confused about how many sig figs to put, would we just want to put the 2 at the end?
That's a great question. So on an exam, am I going to tell you how many sig figs, or how's that going to work? What do we do? We should always try to keep track of sig figs and round our answers at the end of all the calculations to the correct number of significant figures. On the first exam, there are some questions that are specifically testing you on sig figs, and there, yes, you have to get it exactly right. Most of the exams are going to be multiple choice with a few problems where you have to write out and show your work. On the multiple choice, I am not going to try to trick you with sig figs. So if this was an answer on a multiple choice exam, 13.5, the other answers might be like 21.4, 10.9. Would I do 13.519? No, because that's mean.
Say yes.
There are times when I will try to trick you, but I'm going to warn you ahead of time. I'm going to try to trick you with this on an exam, okay? But here, what if your math was a little wonky and your number came up to be 13.4 and you had to choose between those? Would you freak out and say, the correct answer isn't on there? No, you would pick B because it's very close. It's different in that last significant figure. It's essentially the same. Yeah.
Will we also get partial credit for showing work during like those showing?
Yes. The questions where you have to show your work, I will give partial credit. So that's where the longer, hairier problems will come, where you do all this work and then one little mistake. If you pick the wrong letter, then the whole thing's gone. I don't want to do that. I want to reward you for your work, because I look at your work and I'm like, well, clearly they had a very good idea of what they were doing. They just made this one little mistake, so I'll give you 3 out of 4.
I'm sorry.
No, that's good.
But for multiple choice, if you do, and it's like a work problem, if you write down on the side of that like A, B, C, or D, and you show where you're going with that work, could you also potentially get partial credit?
That would be nice, but I have 60 students,
Yeah.
so it's not practical.
Okay.
I do, when I give you an exam, I'm eventually going to return that copy of the exam to you, and so I encourage you to write all over it. Definitely. Show your work, write all over it. Then when you get the exam back, if you got an answer wrong and you showed your work, you can go back and find out what the mistake was that you made. But I can't do partial credit on those. Okay, so continuing this little story, the woman in this example is shocked to find out the ring is fake and returns it. Oh, phew, she wasn't trying to cheat him. She buys a new ring that has a mass of 4.53 grams and a volume of 0.212 cubic centimeters. Is this one platinum? Well, we just did one like this, so this one should be a little easier, right? No, density isn't density. Density is mass over volume. So we're going to take the mass with its unit and divide by the volume with its unit. And again, I'm getting a whole bunch of digits on my calculator, but this time I'm going to think ahead. 3 sig figs, 3 sig figs. This one should have 3 sig figs. So I'm going to write down numbers until I get to the third one. That's the last one. And then I'm just going to copy down the next 2 digits. You don't even have to worry about rounding up or down on that last one. So I'm going to write that down, and then I'm going to round it, and I'm going to get 21.4 grams per cubic centimeters. And if you remember from the table, that is the density of platinum.
Regularly, it's for division or multiplication. It's whatever the sig figs are for the smallest one or for the
Smallest. So you could think of it this way. We never want to have people think that we're deceiving them, right? Fraud in science is really, really bad. So we want to overestimate our uncertainty or underestimate our certainty. So we're looking at all of these numbers, and whichever one is the least precise, that's going to make the answer a similar precision. So like they could all be like 4 or 5 sig figs, and then you've got one number in there that's only 2 sig figs. Well, now your answer just went down to 2 sig figs. So it's the worst case scenario. Is the new ring platinum? We got to answer this. Yes. Okay. This one, hopefully, I started off doing this one wrong yesterday. It was so embarrassing. Try to not do that today. Okay. The density of copper decreases as the temperature increases. This happens for most things. Which change occurs in a sample of copper when it is warmed from room temperature to 95 degrees Celsius? So this is, a conceptual problem. There's no calculation to do, which actually makes some people a little crazy because, well, I could calculate it, but don't make me think about it. So how do you even go about thinking about this? Well, let's think about what density is. It's the mass divided by the volume. The first sentence tells us that the density is going to get smaller when the temperature increases. So density gets smaller when the temperature increases. Okay, so now the actual question, what's happening here with the copper? Is it getting hotter or colder? Hotter. It's getting warmed. So its temperature is going up, so its density has to go down. So they're looking at all the possibilities. The mass, the sample becomes lighter or heavier? That's not possible. Mass is a measure of how much matter there is, and it doesn't matter what temperature it is, it's still the same amount of matter. Okay, so those two are ridiculous. But the last two, so the sample expands or the sample contracts. So here we're talking about what's going on with the volume. The sample expands. Is the volume getting bigger or smaller?
Bigger.
The volume's getting bigger. So the mass is the same, but the volume is bigger. How does that affect density? Makes it smaller. So that's the answer.